Thanks, guys. Yeah, so today we're going to be talking about Kafka and how it's going to evolve in the future. So Kafka has gotten a lot of mileage out of Zookeeper. And Zookeeper is used in many ways in Kafka. So we use it to store metadata. We use it to receive notifications when certain things change. And it's actually, done pretty well at that. So we have a lot of respect for Zookeeper, for the community behind it, and for the authors. But it is still a second system. So it's another thing people have to learn. It's another moving part. All of those things. So what we're talking about today is a new Kafka improvement proposal called KIP 500. That's talking about how we can move beyond Zookeeper and basically use Kafka itself to store our metadata and manage it. So I want to emphasize that this isn't going to be a one-to-one replacement of Zookeeper. So we're not replacing Zookeeper with another system which is substantially like Zookeeper. So it's not about using something like one of the many projects which are similar to Zookeeper, but maybe have a slightly different API, slightly different implementation. It's actually about managing the metadata in a very different way, and a way that we feel will be much more extensible and supportable in the future. Along the way, I'm going to talk a little bit about, how we got here and what direction we've been going. And there's actually a lot of previous work that's been leading up to this. So KIP 500 is kind of like the culmination of a lot of work that the community's been doing for many years. And so to start off, I'm going to talk a little bit about the evolution of Apache Kafka clients. And you guys probably already know already, the client is the thing that talks to the server here. We basically have three kinds of clients. One of them is the producer that will put messages into the system, the consumer that will pull them out, and administrative tools that will do stuff like creating topics, deleting topics, security-related stuff, setting up security settings, that sort of thing. So in the very beginning, we had producers. They would write to topics. That was obviously going through the broker. I'm using this Kafka symbol here to represent the broker processes. We would have consumers that would read those topics. But there was a hitch here, which is that the consumers needed to store the offset that they last fetched from periodically. And we used Zookeeper for that in the beginning. We also used Zookeeper to understand what consumer group we were part of. And understanding this is key to doing things like doing rebalancing when a consumer from a consumer group goes down, and all that stuff. And of course, the administrative tools would also go directly to Zookeeper. So there would be no broker involvement in the administrative tools. So if you wanted to delete a topic or create a topic, you would just basically have a script that launched a Scala process, and that would manipulate the Zookeeper stuff directly. So this was the situation back in like the Kafka 0.8 days. The first, and I guess I should talk a little bit about why there were limitations here before we go on. So first of all, Zookeeper is not really a high bandwidth system. So if you have a lot of consumers doing offset fetches and offset commits, it can really start to bog down the system. And it can interfere with stuff which is also key for Zookeeper to do. And secondly, we're going to talk more about this later, but this is a real obstacle to having effective security, because all of the security that we implemented was actually on the broker, and by going through Zookeeper, you're bypassing that layer of security. So we started to move away from this, and the first instance of this was the consumer group coordinator. So as I mentioned earlier, originally all of the consumer group stuff would just go through Zookeeper. And all of the offset fetch, offset commit stuff would also go through Zookeeper. So you had these end users who were talking directly to Zookeeper. In order to avoid this, we were able to create these consumer APIs. And basically this offset fetch and offset commit became APIs on the broker. And so they were no longer things that you would talk directly to Zookeeper to do, but you could talk to the broker. And then the broker could store this stuff internally in a topic. So 2 things here. We're creating a new API on the broker, and we're storing the data in a different place. It's no longer being stored in Zookeeper, but it's being stored in Kafka itself. So this is kind of an example of Kafka on Kafka, right? We're using the system to store our own metadata here. The second thing we did was basically to do the same for group partition assignment. So we created a similar set of APIs. The join group API, the sync group API, heartbeat API. And so we were able to take Zookeeper out of the consumer read path. And that's really good because then we can scale out the number of consumers more effectively. And we can also basically secure consumers a lot easier. So after this, the diagram looks a little more like this, right? The producer and the consumer are going through the regular brokers, and the admin tools are still talking directly to Zookeeper. So before we talk more, we should have a brief digression about security here. So as Kafka was growing in popularity, there was a greater demand to have security, and in particular, policies that we can enforce at the topic level and things like that. So this is something that we implemented on the broker side through access control lists, or ACLs, we usually call them. So you could have an ACL that would say, like, you can read from this thing or you can't read from this thing, stuff like that. But again, when you go directly to Zookeeper, you're bypassing the ACLs. So it's a bit of a hole in the security model in that sense. So our next goal here was basically to rework the admin tools in terms of APIs on the broker. And in order to do that, we created this thing called admin client. Admin client was similar to the producer and consumer in the sense that it's basically a class which communicates with the broker over well-defined APIs. And so these APIs were things like create topics, delete topics, alter configs. And so we've been reworking the admin tool so that they use the admin client rather than talking directly to Zookeeper. And by doing this, we can do things like give people the ability to create topics that start with a certain prefix, but not the ability to create topics that start with another prefix. Or we can, they can't delete certain topics, but maybe they can create their own topics. So rather than being an all or nothing, security is now a lot more fine-grained. And in fact, we can even have programs which create Kafka topics as part of their regular operations. So it's no longer just something that the admin has to do from the command line. So at this point, the diagram looks a lot more like this, right? You have the producer, consumer, and admin client all going through these APIs and all talking to the broker. And then the broker will manage whatever needs to be done in Zookeeper. So in addition to security, there's actually a lot more benefits that we've only really touched on here. And basically, these are the benefits that you get by encapsulating the data here. So what do I mean by that? What I mean is that the data in Zookeeper is in a certain format, right? And over time, that format will evolve. But on the other hand, people may use different versions of the client. So it's actually really nice to have an API in the middle that can translate, let's say, an older request into the new format which we're now using. And this helps with compatibility because we're no longer directly accessing basically the brain of Kafka. We're actually going through these APIs, which give us the ability to have like a well-defined interface. And we can also validate these APIs. So we can say stuff like, well, you can't create this topic with these certain settings, things like that. And so it became possible to have policies, which is something we really couldn't have when we're directly modifying stuff in Zookeeper. So those are all pretty important things there. So far we've just been talking about clients and how they interact with the system. But it's actually equally important to think about how brokers interact with other brokers or with Zookeeper. And in the case of Kafka, we actually have a lot of interacting to do. So brokers need to register themselves with Zookeeper so that people know where they are. Obviously, we have to manage ACLs. We have to know about what they are. We have this concept of dynamic configuration, which is basically configurations that you can change over time in a managed way and have them changed at runtime. We also have this thing called the ISR, which is basically the in-sync replica set, and this has to do with how we do replication. So this is all metadata that we need to worry about. In order to do this, Kafka elects a single broker to be the controller. And this is kind of a familiar pattern if you've used Zookeeper before. This idea of having a leader, which is elected by Zookeeper, where you delegate certain responsibilities to that node. And of course, controller election is very important for us. Controller election is managed by Zookeeper. So the model that we have here is basically that Zookeeper will elect a single controller, and that controller will update the rest of the system with the changes to metadata that are made. And that's done through certain APIs. I'm not going to go into detail about what they are, but basically the ones pictured in the top right here. So the controller will be responsible for pushing out these updates to the metadata. So even though I just got done saying this is the model, there are actually some exceptions now. One of them is that there are cases where brokers go directly to Zookeeper. And one of them is when changing the in-sync replica set. So currently, the leader of a partition will directly communicate with Zookeeper when changing the in-sync replica set. And this kind of creates a lot of the same problems that we saw with clients, right? Which is that now it's sort of hard to change the format, right? Because what if you have a broker from an older version that's changing this, and it's overwriting the new format with an old one? There's also issues about notifications. We'll get into those later. So one of the things that we've been working on lately is actually creating APIs to avoid having this kind of direct Zookeeper access from brokers. So the model that we'd like to get to is a model where we centralize the Zookeeper access in the controller. So the controller is sort of the node that we're going to delegate this work to. And that gives us, again, a lot of the same benefits we had before. So it's a lot easier to reason about a system where there's a single source of truth, in this case, the controller. And, well, ideally, Zookeeper is the single source of truth, but the controller should be like the bottleneck through which changes flow to it. It's a lot easier to reason about that than having dozens of brokers that are all making changes at once, potentially overriding each other's changes. We have the benefits of better compatibility. And of course, we just have better encapsulation. I should note in passing that there are facilities in Zookeeper to manage concurrent writes. There's basically like a compare and swap type primitive. But again, that sort of makes the system pretty hard to reason about if you start using it a lot. So another important concept here is broker liveness. And this is basically who's in the cluster, right? So this is actually a very important concept in any clustered system. You have to know who's alive, who's part of the system, and what responsibilities they have at any given moment. This is one of the things that Zookeeper gives us currently. And the way that it's done is by maintaining this Zookeeper session. So the Zookeeper session is basically opened when the broker starts talking to the Zookeeper cluster. And the broker will create this node that talks about where it is, how you contact it, and so on. So currently, and that node will contain information like the IP addresses you can use, the rack, and so on. So let's say that a broker actually goes away. In that case, the Zookeeper session will also go away, and this ephemeral Z node will be removed. Now currently, that will trigger a watch, and that will update the controller. And then the controller will push out these updates, basically saying what just happened, that the broker's offline. So again, this seems like a pretty simple system, right? You have Zookeeper here, and basically, whenever the session goes away, then the controller is notified, and then the controller pushes out the updates. So let's talk about, what can go wrong, right? Because that's always the interesting part here. Well, one thing that can go wrong is maybe the node's not down at all, but it's just partitioned off from the cluster in some way. And you've probably heard the term network partition before. Basically, the idea is that, maybe some nodes can see each other, but some other nodes can't. The network partition that we like the most is the total partition, where basically the node goes away. And you could also regard this as being the case when the node crashes or the hardware goes away. Logically, it's out of the cluster, right? No one can see it. And Kafka handles this pretty well, because the Zookeeper session will go away. And then the controller will notify everyone about what's going on and all the good things. Then there's the case of just being partitioned from a broker or several brokers. In this case, there will actually be some potential loss of availability, because you may not be able to replicate. If you have a partition which relies on that other broker, that will not be replicated. But at least you keep consistency in this system. And then, the case which is most interesting for this talk is when you're partitioned from Zookeeper. Well, I guess there's two cases that are most interesting for this talk, but this is one of them. And this case is interesting because your cluster, you will not be regarded as part of the cluster, and yet, nodes can maybe continue talking to you, which kind of creates a bit of an uncomfortable situation. But regardless of, there's potentially some weird situations that can happen, you'll still basically keep consistency here, because the controller will remove you. It will remove leadership of all the partitions that this node has. So again, similar to case 2, we lose some availability, but we still keep the consistency. But then there's a fourth case, which actually we don't handle that well, and which KIP 500 will actually improve a lot, as we'll see. And that's the case of the controller partition. So if you remember from earlier, the controller is actually telling us about the changes that are happening to cluster topology. So if we can't talk to the controller, or if the controller can't talk to us, we miss out on that stuff. But at the same time, we're still regarded as part of the cluster because we keep our Zookeeper session alive. So this is a very specific example of how the separation between the controller and Zookeeper actually creates awkward situations because they're two separate systems. And so keep that in mind. We'll come back to that later. So metadata inconsistency. Logically, we have this model where Zookeeper is the source of truth. Zookeeper tells the controller about what's going on. And the controller then pushes out these updates to everyone else. So in a sense, everybody is getting these updates in an asynchronous way, because they happen first in Zookeeper, the controller becomes aware, and then they're pushed out. So this is kind of the ideal model of what we would like to happen. But in reality, though, this doesn't always work, because there may be cases where, again, if you have a partition, the controller will try to send out the information, but it simply won't be received. And so in this case, you can actually end up with divergence. And so as a last resort, sometimes people have to actually force a controller election. And there's a way to do that from within Zookeeper. So this is actually kind of frustrating, right? Because you would really like the system to always know whether the metadata is consistent, even if there's some weirdness going on at the network level. And there's a second reason why this is annoying, which is that when a new controller comes up, we actually have to load all of the metadata from Zookeeper. Because remember, the metadata is not stored on the controller. The metadata is stored on Zookeeper. So when you load this metadata, I'll go to the performance issue here. Again, when you're loading this metadata, the complexity is ON, where n is the number of partitions here. So as your number of partitions increases, this loading time will increase as well. And this loading time is actually critically important because while the controller is loading the metadata, it can't be doing things like electing a new leader, stuff like that. So that, again, can lengthen the period when the system is unavailable. I should note in passing that controller election doesn't necessarily create unavailability. It only creates unavailability if you needed the controller to do something during that time. So it's not as bad as it may seem, but it still isn't good, right? In order to scale, we actually would like to get rid of this ON behavior. And another ON thing is pushing all the metadata, right? So as the number of partitions grows, that metadata will increase. It really kind of sucks to have to tell someone all the metadata every time you do this election. And this complexity here, obviously the number of brokers will factor in because we have to send this information to every broker. So, how can we get around this problem? Well, I guess I kind of gave it away with this slide title. But the solution here is to actually do something more like Kafka's users are doing inside Kafka. Specifically, we want to see metadata as an event log. So rather than sending out snapshots, we'd actually like to treat it as a log. So I'll give an example here. Like, if you treat metadata as an event log, then each change to it can become a message. So for example, creating a topic becomes a message, deleting a topic, and so on. And these changes can be propagated to all the brokers in the same way that we propagate changes to consumers. The nice thing about having this log is that there's a clear ordering of what's happening. And we can also send deltas rather than these snapshots. So for example, if I read up to 925, then I don't need to be sent everything. I just need to be sent the updates that happened after 925. It's also easy to sort of quantify what the lag is. How far behind are you actually? Well, if you know the offset, then you can have that information. So, traditionally, Kafka has these consumers, they consume at an offset, and they're consuming from the brokers. In this case, we're actually talking about the brokers that are consuming. So, but what are they consuming from, though, in this case? Well, it's the controller. So the controller will maintain this metadata log internally. But how do we, implement this controller log? So if you recall back to the earlier slides, we were able to implement the log which stored the consumer information just by using a regular Kafka topic. It was nothing special. Well, it has some underscores before it, but it's not that special. But in this case, we actually can't do that because right now the controller is involved in choosing the leader for partitions. But this doesn't really work. We have a circular dependency when we're dealing with metadata. So what we really need is a self-managed quorum here, where there's not a dependency on an external system to choose the leader. The nodes should be able to choose their own leader. And this is actually where Raft comes into the picture. So the main property that we really like about Raft for this application is the last one, right? The fact that leader election is by a majority of the nodes, rather than being done through an external system. Aside from that, though, actually the replication protocols are not too different. So Raft has terms, Kafka has epochs. They're pretty similar. The push-pull thing is interesting. So in the traditional Raft context, changes are pushed out In Kafka, they're traditionally pulled. But it turns out this isn't actually, it's not that big of a difference. You can actually adapt the system pretty easily. So let's talk about the controller quorum a little bit more here. So how do we choose the active controller? Well, first of all, why do we even have multiple controllers? Well, the biggest reason is we want high availability. So we want to actually have the ability to fail over when the controller fails. But secondly, by having a quorum, we can actually take advantage of some of the properties of Raft here. So we can just say that the leader is actually just the active controller is just the leader of the Raft quorum. And the active controller is the only one that can write to the log. So the number of nodes that we'd like here is basically going to be very similar to Zookeeper. So we're probably going to want 3 nodes, maybe 5. We're probably not going to want to go to too many nodes in most cases. So when I said we weren't going to build a better Zookeeper, I kind of lied, because we sort of are. But not in the sense that we're creating a general purpose system, only in the sense that we want to have a replication system which is vaguely reminiscent of Zookeeper. And it turns out that this gives us practically instant failover, because Raft election is pretty quick. And furthermore, the standbys have all the data in memory, so they don't have to load it from some other place. And another way that failover is instant is in the fact that the brokers don't have to refetch everything. And this ties in with what we talked about earlier, which is that if the broker knows the offset that it read up to, it just needs to read the offsets after that. It doesn't need to refetch everything in the world. And another advantage we can have here is we can actually cache this metadata to disk. So when you're starting up your broker, maybe you actually don't want to have to refetch everything. Now, I will note in passing that there are cases where you probably do want to refetch everything. Maybe your disk was wiped out, or maybe you're just so far behind that you don't want to replay all the deltas. But we hope that that's the exception rather than the rule. So these sort of things are going to become increasingly important as we start adding more zeros to the number of topics, the number of partitions that Kafka supports. And as Kafka starts scaling out, it's critical that we get rid of the ON behavior in the system. And so let's talk a little bit about broker registration, which we discussed earlier in the context of how it works now. And of course, broker registration is just the act of building a map of the cluster. So in the post-KIP 500 world, brokers just send heartbeats to the active controller, and the controller can use this to build a map of who's in the cluster. And the controller can also use its responses to tell brokers things about what they should do. Like, for example, maybe they should be fenced if there's already a broker with that ID and stuff like that. Fencing is an important topic in general. So if brokers can't keep up with the metadata updates that are happening, they need to be removed from the cluster, because otherwise they're going to be propagating really old information. And brokers should also self-fence if they can't talk to the controller. So this closes off sort of a lot of the problem scenarios that we've had in the past. There's a lot of different types of fencing in Kafka, and I couldn't possibly talk about all of them, but this is a very important one. So let's talk a little bit about network partitions. We obviously have the same case we had before, where something's totally partitioned. The behavior hasn't really changed. If you can't contact the controller, then you will be removed from the cluster, as is appropriate. The broker partition hasn't really changed either. Same behavior there. But in the case of the controller partition, which was a problem before, it's actually not now. Because if you can't talk to the controller, then you can't send heartbeats. And so therefore you can be removed from the cluster and not be causing problems as sort of a zombie. So this is actually an example of where the post-KIP 500 system eliminates some metadata inconsistency. And of course, we don't have the case we had before where you can't contact Zookeeper because we don't have Zookeeper. So let's switch gears a little bit and talk about deployment. I think deployment is one of the things that people are most excited about when they think about getting rid of Zookeeper. And I do understand why. Again, not to really knock Zookeeper, but it is a separate system. It's another configuration file with a different format, different stuff in it. It's another set of metrics, and another set of admin tools that you have to learn. And finally, and perhaps even worst of all, it's another set of security configurations that you have to master to really secure your system. And it's kind of alarming how many people are running without Zookeeper security right now. So definitely, getting everything under the same security umbrella is really going to help. So when we talk about how controller nodes are going to be deployed, there's actually two options that we're going to support. One of them is a shared controller node, where the controller is actually co-located with the broker. And this is kind of similar to what we have now, where a node that is a controller also has broker duties associated with it. The other option that we're going to support is having separate controller nodes. And this also has a precedent in the sense that typically bigger clusters will run separate Zookeeper nodes to avoid having the performance of the brokers negatively interact with Zookeeper. So both modes I think will be useful, and I think it will depend on the size of the cluster and maybe what kind of hardware you have, stuff like that. For small clusters, co-location I think will be very useful. So I've talked about a lot of stuff, but what's the roadmap for actually doing this stuff? Pretty important question. So there's three basic phases here, I think. One of them is that we remove the client-side Zookeeper dependencies. And this is actually almost done. So we've been creating APIs for the last stragglers who still access Zookeeper directly from the client side. We haven't yet deprecated direct Zookeeper access, but that's happening soon. The phase after this is to remove the broker-side Zookeeper dependencies. And in this phase, we actually will try to centralize the access to Zookeeper in the controller. And this will involve creating some broker-side APIs, sort of in a parallel echo of what we did on the client. I think this phase should also involve fully removing the Zookeeper access for the tools. You may ask why we didn't do it in the previous phase. And the answer is, we try to have a pretty generous deprecation policy in Kafka. And finally, the final phase is this controller quorum, and basically reworking the controller in terms of it. And this includes implementing Raft as well. So let's say, once we've implemented all this stuff, you're going to need a way to upgrade to it. And this is a problem because right now you probably have tools running around which are directly accessing Zookeeper. You have brokers running around accessing Zookeeper, and you have a lot of state in Zookeeper. So if you were to try to jump directly to a KIP 500 release, it wouldn't be really possible to do that through a rolling upgrade. And you guys probably already know this, but a rolling upgrade is one in which you upgrade nodes one by one, and there's no actual downtime. And this is something Kafka has supported for a long time, and it's very important to us. So in order to keep that working, we have this concept of a bridge release. And in the bridge release, there's no Zookeeper access from the tools, and there's also no Zookeeper access from the brokers except the controller. And the rationale behind this will be apparent in a few slides. So let's say you're doing this upgrade to a post KIP 500 release. You would start from this bridge release, which remember has no Zookeeper access from tools and no Zookeeper access from brokers other than the controller. And the first thing you would do is you would start the new controller nodes for the release you're upgrading to. Now that quorum will elect a leader, and it will claim the leadership in Zookeeper. So basically, the new controller will take the leadership and maintain the leadership throughout the upgrade process. Now, at this point, you can start upgrading the nodes one by one, just as you usually would. And the reason this will work, of course, is because all of the Zookeeper access is going through the new controller. And so basically it's handling all of that. This also means that the new software will need to know how to send these old leader and ISR messages to the existing nodes. And finally, of course, once you've rolled all the brokers, you can decommission the Zookeeper nodes. So in summary, it is going to be possible to upgrade to a post-Zookeeper release with zero downtime. So wrapping up here, Zookeeper has served us pretty well. And what we're doing here is not so much replacing Zookeeper as switching to a different paradigm, a different way of managing metadata that we think will be much more effective. And these changes have been going on for a long while. And there are more reasons to do it than just scalability or even just deployability. There's also the improved encapsulation, the improved security, and the improved ability to upgrade and to freely change our internal formats. So those things are all important here, I would say. And I think this is a great example of how managing metadata as a log is much more effective, because it sort of eliminates this need to send full snapshots. And as the size of the system grows, and we expect Kafka to really grow over time, as people start using more and more data, more and more topics, and so on, it becomes more and more important to have the good properties of a log, to basically have deltas rather than sending the full state, to have caching, to be able to know what the ordering is for metadata changes. We also want to improve our availability, to improve controller failover, to improve fencing, and basically be more scalable and more robust. And along the way, it's important that this metadata log be self-managed. And I sort of touched on why that is, and why that needs to be the case here. And finally, it'll take a few releases to fully implement KIP 500. So there's going to be additional Kafka improvement proposals for some of these APIs, for Raft, for how we're going to handle metadata. So KIP 500 is kind of like the overall roadmap, but there are going to be more detailed proposals to come. It's very important to us, and really, the whole community is very interested in rolling upgrades, and we are going to support those. So we talked a little bit about how, and how that's all going to work. And so in conclusion, we believe that once this is implemented, Kafka will need no keeper.
So we got about 10 minutes for questions.
Thanks.
So you mentioned about the Raft, right? So is it an external service system, or is it going to be implementing that?
We're going to implement Raft in Kafka itself. And the reason for that is, Kafka is a system for managing logs. And so we think Raft is kind of like part of our core competency. If you're a system managing logs and you use another system to manage your logs, it's kind of bad.
I see.
And all the usual software engineering reasons apply.
So how do you make sure that the Raft consensus is, the participation of the Raft consensus is only done by the brokers, which are in-sync replicas, and not the ones that are already taken out by the controller?
Sorry, I didn't quite get that.
So you have controller, and you say you have 10 brokers, and controller is keeping in track of the in-sync replicas for all of these brokers, and one of the broker never actually received the metadata. So controller would possibly remove that from the in-sync replica group. Is that correct? So in
In most cases, the leader will remove a broker from the in-sync replica set, not the controller. There
Okay.
are cases where the controller will do it, but in general, it's normally the leader of the partition.
Okay, so in that case, suppose the leader actually removes the in-sync replica, a broker from the in-sync replica, and the leader dies, there will be a consensus, raft consensus, that would elect a new leader.
I think we're talking about two different things here. If we're using Raft, we're not using the ISR, right? So there's going to be basically two replication systems. One of them, the one we have now, and the other will be Raft.
Oh,
And Raft does not have, well, I mean, it probably does. It does have something similar to the in-sync replica set, but it's not going to be the in-sync replica set you know through Kafka. It's not going to have all the same properties exactly.
Got it, thank you.
Way over there, really?
What if you have only two Kafka brokers and something bad happens with network, and who will be controller?
So in general, if you only have two nodes, then you can't really have, I mean, you can have a Raft quorum, but it'll be of size either 1 or 2. And that's basically not going to provide any redundancy.
Let's say you have 4, 6. I mean, it's example. Let's say you have 4 brokers, and it separates 2 and 2. Who will be controller?
So if there's a network partition and it's 2 and 2, then you can't form a quorum, basically, right? Yeah. Oh, I'm sorry. So first of all, I'm assuming that you have an odd number of controller nodes, because that's how you would normally deploy it. But even if you did choose to have 4 nodes, the rule is going to be basically you need a majority, right? So let's say your quorum is size 3. That means you need 2 nodes for a majority, right? If your quorum is size 4, then you would need 3, I think. Wait. But the point is, at a certain point, you have to sacrifice availability, right? If you can't form a quorum, then you must sacrifice availability. And this is the same thing we have with Zookeeper right now, right? Let's say you have a Zookeeper quorum of size 3 and you lose 2 nodes. They go away. Then your quorum is done, and your system is down until you can bring up at least 1 more node, right? Yeah, so it's not changing, basically, in that regard.
Are you expecting if you have a pool of 10, 20 brokers, they'll all be participant potential controllers? Or do you have to explicitly set these 3, these 6 could be controllers?
That's a good question.
Well, I'll just duke it out and say, hey, 5, that sounds like a good number, and choose?
Yes, so that's a good question. And the answer is the second one. So there's only going to be certain nodes that you would nominate as potential controllers, which again is kind of similar to how we do Zookeeper now, right? I mean, you're not going to run a Zookeeper node alongside every broker in a very large cluster. You wouldn't have a controller node on every broker in a post-Kip 500 cluster. But good question.
Anyone else? All right, thank you, Colin.
All right, thanks.